$1. All right, good morning, everybody. How was your weekend? Amazing? Good? Terrible? You know, in a class of more than 30, there's going to be the full range, right? So I'm sorry if it was terrible. I'm glad if it was good. And all of the appropriate emotional responses. We've got a lot of math today. Okay. And I'm sorry, I learned earlier this morning that Math 5B students might have an exam. Right? So, yeah, well, good luck. All right, 5B. Yes. All right. So, I don't know if you noticed last time I kind of did a problem in general, right, as a template for you to follow for when we put an object on a hill, or what we call an inclined plane. Now we're going to do the same thing, but we're going to have more than one object, and we're going to attach them together with rope or string or something like that, and we're going to introduce a pulley. So this is like first time for the force of tension, first time for a pulley. Lots of firsts right here. But again, as a example or template for the process. Newton's second law, problem solving, is all about the process. You develop the equation every problem you get. There's no shortcut there. You got to draw the free body diagram. You have to write down Newton's second laws correctly and go through that process. And it's that process you'll want to avoid, because it'll feel like it's taking time and it requires a lot of thinking and a lot of physics and concept. But you got to fight through that, because in the end, it's actually the shortest and quickest way to do the problems. We don't sit around and come up with the longest way to solve these problems, right? These are the established shortest ways to do these problems. Okay, one feature about tension that we really need to talk about, okay? In physics, we are going to give our ropes and our strings, they're going to be physics string. So what do you think about that means about its mass? We're going to say it's massless. Now, you guys are going to call me out. It's got mass. Yes, it does. And if you remind me, you'll have to remind me on Thursday next week. Next Thursday, not this week's lab, but because we do lab 6 first before we do lab 5. But when we get to lab 5, I can show you real physics string, like no joke, okay? I'll teach you what actual physics string is, okay? But for now, we're going to say it's massless, okay? We're also going to say it doesn't stretch. And by saying it has no mass and saying that it doesn't stretch or break, it means that the force is going to be the same all the way along it. And we can just apply Newton's third law. But one thing that's always true about tension is that tension always pulls. Can tension ever push? As soon as I try to push, right? The rope or the sling or the chain or whatever's in the problem just goes slack, doesn't it? Okay? So tensions can only ever pull on objects. And it's an important thing to remember as we're going about doing stuff. So what does this look like? Connected objects. We're going to throw on an inclined plane, because why not? We've done an inclined plane already. That was too small of a line. Let's try that one. All right. So we seeing things. Oh, look at that. We're seeing things on the screen. Stuff does work. Okay. That was bad. Let's try that again. Still bad. There we go. All right. So let's put, we're going to put one object. It doesn't matter what these, it could be anything, right? But we're going to put a couple of objects in our system, and we're going to run a rope or a string or something, right? So this could be like a weird kind of elevator or minecart or ski lift. Like, there's a whole bunch of systems that involve objects connected together through some force, some medium, and they're moving together, they're doing things together, okay? Now, the pulley in this problem, for now, is going to be a perfect physics pulley, meaning that it doesn't have any mass, it doesn't have any friction. Its only job is to change the direction of the tension in that rope. I was going to say don't worry. No, you should be worried because around chapter 11 or 12, we're going to start doing real pulleys. Maybe it's chapter 10. Okay? All right. So this is the situation we have. Remember that a free body diagram tells you nothing about how a system is going to move. We don't know anything about the velocities here. All we can predict is how the motion is going to change. Our goal is going to be to find the acceleration of this system, sort of like, really, we can find out information about forces, or we can find out information about acceleration, and that's it with Newton's second law. If I wanted to find out how fast mass number 1 was going when it, got to the top of this incline, as soon as I start asking how fast, what toolbox do I need to use? The first unit's toolbox, the kinematic stuff, right? Because it had velocities in it. If I want to know about time, that's first unit, right? But when it comes to acceleration, I can either use kinematics, because it's got acceleration in it, or I can use Newton's laws, right? So kinematics doesn't say anything about forces. So if forces are involved and you're doing a force analysis, well, now you know you're in the toolbox of Newton's laws. Okay, so now we go through the same process. Again, I'm harping on this process. The process is so important. Visualize, strategize, do it, check it. And in visualize, what are we going to draw? Free body diagram. Okay, it's the established method for making sure that we don't miss things. And in putting these forces on our objects, what's the key question we want to answer? These are all good questions. It's not the key one, no. What objects are pushing or pulling on the objects in our problem? Remember, if you can name the other object via Newton's third law that is pushing or pulling on one of those, then you know you've got a real force. If you can't name the object, there's a good chance you're making up a force. For example, is there a force that pulls mass 1 down the slope? Yeah. And a lot of students will make a mistake and go in, okay, all right, well, don't do this. And say, okay, well, there's a force there, right? And they'll keep going, and then they'll draw gravity in it, right? Because you just kind of know, oh, well, the gravity pulls it down. Well, I drew gravity twice there, didn't I? Right? And there's a mistake. Now, eventually that will become a component of gravity. That's true. But you want to be able to name the object and set the direction of the force correctly. So we have 2 objects in this problem, which means we are going to have 2 free body diagrams. We are going to have 2 applications of Newton's second law. For every object in your problem, you have to set up a new set of equations. So let's do mass number 1 first, because we've kind of been here before, right? Name either a force or an object. Well, if you name the force, tell me the object, or the other way around, stuff acting on mass 1. Gravity, which is caused by planet Earth, and then the surface itself. Is that what you meant by the ground, right? Like the hill, okay? Because they're coming into contact with each other. What do we call that one? Normal force, and it's perpendicular to the surface, okay? Tension from the string, right? So which way is tension pulling? Tension never pushes. Up or down the slope? It's pulling up the slope, right? That string can't push M number 1 down the slope, right? And you might be sitting there going, well, but what if M1 is winning, right? What if M1 has such a big mass that it's pulling M2 up, right? Wouldn't that mean tension is pulling down the slope? No, it doesn't. Tension can only pull, right? And what's the only direction that string can pull on mass number 1? Up the slope, right? Okay. So we don't know who is winning. Like, one of the things we're going to try and find is who is winning, right? Which direction is the acceleration here, right? We don't know who's winning, and so therefore we got to follow Newton's laws about what can push or pull and all that kind of stuff. So it could be that it's accelerating and or moving down the slope. That will come out in the wash as we look at the force of gravity acting on this thing and so on and so forth. Okay, are there any other objects pushing or pulling on mass number 1? No. We've got the string, we've got the surface, and we've got the earth. Nothing else is indicated there. All right, mass number 2, same treatment. We've got to name objects that are pushing or pulling on mass number 2. Name some.
Gravity.
Okay, so gravity is the force and earth is the thing. Tension, which way is the tension acting? Up, right? Can only pull. Now, because this is physics string and because that is a physics pulley, meaning that it's massless, right? Doesn't have any inertia of its own, string doesn't stretch or break, we know that those two tensions are identical. Tensions are the same all the way along that string. Again, we'll cover how that changes when you start using real stuff later.
Draw a free body diagram, you would pick how your axes are tilted. Would we have 2 coordinate systems for each?
Yes, so we're about to do that, right? I decided to push off the coordinate system definitions after we had found all the forces. But yeah, right? You end up with separate but consistent coordinate systems, and I'll explain what I mean by that in a second. Are there any other objects acting on mass 2? No, right? Okay. Nothing in the horizontal direction? Yeah, there's no contact, there's nothing pulling it that way, we're good. Okay, so Liam brought up the coordinate system thing. So remember, I told you to set a positive direction in the direction that you think the acceleration is happening. Now, we're after acceleration. The things hopefully that we're given are these masses. We give the angle, we give the 2 masses, right? We know little g. So we're after the acceleration here. So if you're not told, I think some of your homework problems say, assume up the slope is positive, I think one of them said, or something like that, right? I could be thinking of a different class. Just realize that in a situation like this, you have to guess, you have to pick, you have to commit to what direction you think the acceleration is happening. Again, the change in motion, not what it's doing, but how it's going to change. And if you're wrong, it's going to be okay. You'll get a negative sign compared to, say, somebody else that chooses a different direction. Okay? But let's take a look at mass number 1. I can only think of 2 directions the acceleration really could be. What 2 directions? Kind of up or down the slope, right? Okay. So now we need to pick. Who do you think's winning? M1 or M2? M1?
Let's say M2.
M2? If M2's winning, then that means the acceleration, the net force, will be sort of in the direction of M2. So regardless of whether M1 is moving up or down the slope, right? So if M1 were moving down the slope initially, but it's accelerating upwards, that means it would slow down, right? If M1 were moving up the slope and the acceleration were up the slope, it means it would speed up, right? But we're just trying to guess a direction for sort of the net force and therefore the acceleration in the problem. And should we go with M2? M2 wins, so to speak, okay? Again, it doesn't matter, okay? It's going to depend on a lot. Well, you guess. What do you think it might depend on who wins here? Mass, definitely. And the relative mass between, like if they're equal, then it's not really the mass, it would be what? The angle of that incline, right? Because if it were flat, then M2 would definitely win, wouldn't it? But as this thing gets steeper, you'd expect M1's gravity to start working more and all that kind of stuff, right? So you can sort of think ahead about what this thing might do. And so let's just guess. And again, this is an assumption that we're making, right? the acceleration will be up the slope. Once you identify your choice for acceleration for one object, be consistent for the other object. What do I mean by that? If the acceleration for mass 1 is up, what direction does the acceleration for mass 2 have to be? It has to be down. Remember? We've got a tension in this problem, okay? And if we go over something like a pulley, is my hair doing funny things? Okay, right? Then whatever's happening to mass number 1, mass number 2 has to fall, right? We can't have accelerations be like this, because then the string would go slack, right? So make sure that you are consistent. This is what I mean by consistency. It's physically possible, the thing that you are setting up. Okay? So if acceleration's up the slope for that side, we're going to set acceleration down for mass number 2. Okay, now we apply our rule of thumb. The safety valve on all of this, right, is to make sure that our coordinate system points which way? Along with the acceleration. This simplifies our mathematical steps later. So that means I'm going to say positive x is up the slope for mass number 1. And then I have to make positive y at 90 degrees to it. So I'll just pick away from the slope. Why not? What direction will positive y be for mass number 2? Look at it and think. Now answer. Down. Why does positive y have to be down? Because the acceleration is down. This is where you'll feel kind of uncomfortable, right? Your brain will rebel just a little bit. You're like, but positive, up is always positive. You can do it that way, but you run into more problems with your signs. You'll just have to trust me on that. I'd rather your brain get used to a new way of thinking about changing your definition for which way has to be positive rather than have you chasing sign errors all the time. Okay? But there will be people on YouTube and various places that maybe ChatGPT would choose to point up, and as long as it's consistent, it'll be okay. Okay? Yeah.
Do you know the angle of x, like positive x and y is up?
So are you saying like, can you make this plus x instead of plus y? I don't care. It's a label. I really don't care. Most people rebel at me if I put positive x for a vertical thing. That's one part of the brain I'm unwilling to go to. So I'm willing to change your definition about which way is positive, but most people will go, oh, positive x down. Ah. Yeah, you can call that x. You can call it Frank for all I care, right? It's just a label. Okay, so, and do I need an x-axis for mass number 2? No, there's nothing going on in the horizontal direction, so I don't want to cloud up my diagram with anything extra, right? Okay. All right, so are the free body diagrams here complete? What's required for a free body diagram to be complete or done? The forces need to be labeled, right? Indicated and labeled. And the axis needs to be defined. Those are the two things that you can't get any traction unless those two things are true, right? The acceleration is not required, but certainly very helpful for making sure you set your directions correctly, right? That's our visualized step, right? Now we move into strategy. We're trying to problem solve. We don't even remember what we're trying to find anymore, but we can still write down Newton's second law for both of these objects. Okay? So there's Newton's second law right there. And I'm going to go ahead and let's see. We need to be kind of careful here. We have two masses. We have mass number 1 and we have mass number 2. Both of them are going to have equations in the x and y. Mass number 2 won't have x, but we'll do this for being complete everywhere. Okay? And as a template, as an automatic thing, you can just write down. How do you start Newton's second law? MA equals. It always just starts there. So I'm going to write m1a1x equals, and I'm going to write m2a2y equal. I'm m2. Darn it. It's Monday. m1a1y. Just again, applying this to mass number 1, right? ma. Well, what mass is it? It's mass number 1. What acceleration am I talking about? The acceleration of mass number 1 in the x direction, then again in the y direction. All right. And then over here for the x, I can do m2a2x equals m2a2y equals. I'm just, again, Newton's second law, remember Mr. Balogh writes it backwards. You start with ma because it's automatic. It's easy. Just put it down. Okay? We do not have to check the direction of the acceleration. Why don't we have to go in here and check the acceleration, see if it's positive or negative? We set it up. Remember the rule of thumb? We set it up so that our positive direction always follows the acceleration. That's why it allows this to just be automatic for us, right? Okay. We're all set up, ready to go. What do we have to get down now? All these forces, right? Okay. Now, this brings up a bit of an issue that we kind of have to now double back into our visualization to fix. One of the forces on the screen is not playing nice with our coordinate system. One of the forces does not point in just x or just y. It has components. Which force is it? Excellent. It's the gravity on m. Oh, I messed up there, didn't I? This is m1g and this is m2g, isn't it? So m1g, the weight of object number 1, is pointing in both an x and a y direction. We've been here before. Remember, Mr. Balogh likes to kind of put a coordinate system down to just orient visually. And then we come in here and say, okay, we know that gravity is going to have a component pointing down the slope and into the slope. We know from geometry that those two angles are equal. So what does that mean for the y component of gravity? Is it sine or cosine? This component along the y, negative y-axis right here. Sine or cosine? Cosine. A lot of you were going, cosine? That's because it's a Monday, and that's because you've been programmed to think that y means sine, haven't you? Like your brain has made sort of a shortcut there because it always seemed to be true in math, right? Got to look at where the angle is, touching, not touching. Is that component touching the angle? Cosine. mg cosine theta, and then therefore the other one is mg sine. And then you'll make the mistake when you try to copy them over into your equations, right? You'll see the x direction, and you'll write mg cosine instead of mg, right? So just beware, right? You've been programmed incorrectly through your mathematical career to think that sine always means find the y or opposite side. It doesn't. It totally depends on where the angle is. Okay, so now I can come in here and start writing down my forces. In the x direction, so we are only looking along this line. The x direction for mass number 1, how many forces are there? Tension and mg sine theta. Those are the only two along that line. Notice how I left space. Why did I leave space? I've got to go put the signs in. I've got to get the directions in, right? So what direction is tension pointing? Positive x or negative x? Positive x. And mg sine theta? Negative. What steps am I following here? What's my algorithm? First thing I did was write down what the forces were. Notice how I separated out writing down what the forces are from the step of what direction are they pointing. Will you get to a point where you could do both of those steps at the same time? Yes, you'll get there. but your brain needs a little bit of the training wheels of, okay, what forces do I have? Because it's really easy to miss a force, isn't it? Unless you're being really careful. So imagine you're just looking at the horizontal, just write down what those forces are, do that step, and then go, okay, which way is t pointing? Okay, which way is mg sine theta pointing, right? Separate that out so your brain gets used to thinking about both of those things, and eventually you'll be able to do it at the same time, right? But it's really helpful for your brain to break those steps out. All right, in the y direction. So here, I'm just concentrating along this line. How many forces are there? Looks like there's two. One of them's labeled n. What's the other one? mg cosine theta. Now I go back and do the directions. What direction is the normal force? And mg cosine theta pointing along the negative y-axis. Okay, so there we go. Got my forces down, and I've got my directions established. Okay, for mass number 2 in the x direction, how many forces are there? 0. Which means that a2x, unsurprisingly, is also 0, right? Okay. And while we're here, is there another acceleration that is 0? By definition, because we chose it that way.
Mass 1, the y component.
The y component's acceleration is 0 for mass number 1. We made sure that the acceleration of mass number 1 was only going to be in which way? The x direction, right? Okay, we tilted our coordinate system, paid that price for the freedom to be able to make sure that that side of that equation was 0. Okay, m2a2y. All right, so be very careful here. I want you to do this right now in your notes. You can just do it yourself, or you can look at each other for help. Doesn't matter to me. Write down the forces, and then get their directions. Just kind of do it right in your notes. Feel free to show people next to you, or if you're feeling lost, look at the person next to you and go, help. So the two forces are what? Tension and the weight of mass 2, right? So m2g. What direction does tension point? The negative direction. But Mr. Balogh is pointing up. Yes, true. What way did we say was positive? Down. Mr. Balogh, this is so confusing. Why don't you just do it the other way? Just because something points up, does that mean it's positive? No, right? That is such a reflex. It is such a habit that is ingrained in your brain. And every time I talk to a math teacher, I just want to take them by the shoulders and shake them. Shaken mathematician syndrome, right? About just please stop teaching your students that up is always positive. It depends. It always depends. I've watched, I had to have my roof analyzed by an engineer to get some solar panels put on it many years ago, because they had to determine whether or not the roof could support the load of the solar panels, blah, blah, blah. And I asked for the actual work that went into the analysis, because I told them I was a physics teacher, I wanted to see it. And so the engineer came back, sat down with me, went through all the calculations. And in fact, he was rotating his coordinates like at every joist, right? Where two members would come together, he'd rotate his coordinate system so he didn't have to pick off too many vector components, right, and go through. I was like, I could do this. Why didn't I just do this? And he said, do you have a license? I'm like, no. So, cost me lots of money, but it was good. I checked his work. It was awesome. All right. So yeah, this is a common practice, rotating those coordinate systems and giving up on what way is positive. Your diagram will help you. Okay. My gosh. I mean, it looks so innocent, doesn't it, Newton's second law? Short, 3 things in it. How bad can it get? Pretty bad. What if you had, I don't know, a third object attached to these? How many equations are you going to have now? 2 more, 6 total, right? Okay. Now, granted, one of these equations is true but useless. 0 equals 0? That's a nice equation, isn't it? Yeah. I can take the integral of both sides of that, no problem. Right? You want me to do a differential equation on that? Psh, piece of cake. But, like most mathematics, not useful. All right. What were we solving for? What were we looking for? Did anybody? Oh, acceleration. Thank you. Right? Like, we're looking for the acceleration. Now, it seems like there's 2 accelerations here, isn't there? Yeah. A1x and A2y. What do we know about A1x and A2y? They are connected, meaning that they are identical, right? Because it's physics street, because it's not stretching or breaking or doing anything weird, we know that those 2 masses will change their motion exactly the same way. Okay? So, I am left. Now, the y direction equation for mass number 1, does it have any acceleration in it? No, so it's not useful for solving the acceleration of this system. So what am I left with? M1a equals t minus mg sine theta. And then I've got an m2a equals m2g minus t. I sort of cleaned up a little bit there, right? Took off the implied positives. I'm doing math now, right? And this is going to be an algebra problem, so just trying to, I reversed the order of the right-hand side of that equation because it was a lie, but it was beaten into me in school that positive things go first and negative things go second. Again, that's opinion, that's not math. All right, so I'm solving those 2 equations for acceleration. How many unknowns do I have? 2. By the way, what step am I in now? This is the do it step, isn't it? Okay. For those of you that have just been waiting for 25 minutes for the point where Mr. Balogh, can I just please do some algebra? Stop making me think about all this physics stuff. Do you ever imagine you'd have a class where you'd beg to just do some math? You're welcome. All right, anyway. I've got 2 equations, 2 unknowns. The unknowns are a and t, aren't they? I haven't been given any information about t, which means I got to get rid of t. So either I need friends in high or low places to take those t's out, or I got to do some math. So this is taught so many different ways in various high schools. I'm going to solve the second equation for t and substitute that one into the first equation. You might have been taught to solve them both for t and set them equal to each other. It's exactly the same thing. So solve for t, we'll do it in purple. Let's see, that's going to move t over, and then I move the m2a over. And when you move something across the equal sign, what happens? I've already lost you. The sign flips, right? This is a shortcut to add the thing to both sides, add t to both sides, right? Subtract m2a from both sides. I just think of it as, if it's going to the other side of the equal sign, it gets a sign flip. All right. And then that t gets put into here, doesn't it? So now I have m1a equals t, which is m2g minus m2a. And I still have my mg sine theta. I'm doing this fast because it's not math class. The m2a, I'm going to move over to the other side of the equal sign. So what happens to its sign? Did I do something wrong already? equals m2g. I do things wrong all the time in math. Sine theta. And now, how do I get this a all by itself? Factor it out. You guys didn't want to say it because you were tortured with it so often in algebra class. Right? I've got to factor that common factor of a out. m1 plus m2 equals all this junk. This is an m. Well, I lost an m1 somewhere. m1, that's an m1, 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 sine theta. So now my acceleration is going to be m2g minus m1g sine theta all over m1 plus m2. There it is. Ay. That's it's a lot of math for Monday. Okay. What's the last step everybody wants to forget? Fourth step in the problem-solving process. Check it. So how do I check it if it's got no numbers in it? Well, we start playing around with what this thing's trying to tell me, right? Interestingly enough, there's a minus sign in here, right? So what's m2g? What does that mean? It's the weight of mass number 2, right? So how much gravity is pulling mass number 2 down, isn't it? Symbolically, m2 times g is the weight of object number 2. Okay. What's m1g sine theta?
That is the gravitational component of...
Good. It's gravity pulling down the slope, isn't it? Gravity can't pull it directly down. It can only pull it down the slope, which is why we got the angle in there. But notice that the weight of object 2 and the part of the weight pulling object 1 down the slope, what are we doing with those two things? We're subtracting them. Is that what's are they fighting each other? Is the weight of object 2 fighting the weight of object 1? Yeah, right? They're in like a bit of a tug of war, aren't they? And if m1g sine theta is bigger than m2g, what's going to happen? Acceleration is going to be down the slope and up, isn't it? And we will get a negative sign. Why will we get a negative sign? Because we said up was positive, right?
Yeah.
What if your friend is solving this problem and shows acceleration down the slope? What do you think their solution might look like? It would just have this flipped. Okay? That would be it. And you'd look at it, oh, we got two different things. The earth is falling. No, you got the same thing. It's just you're disagreeing on which way is called positive. All right. If m2g is bigger than m1g sine theta, then this whole thing's positive, which means it's going the direction we assumed it was going to be going. Okay? The angle in there, m1g sine, I mean, if m2g doesn't exist, if the mass of m2 is 0, what do we get? Do you recognize that? Remember g sine theta?
Yeah.
That was the answer we got for the inclined plane last time, wasn't it? So there's another check that you can do. Obviously, solving your homework, working on the exam, you're going to have numbers, right? And you might be able to go back and check and see if some of the numbers are consistent, that sort of thing. Doing it symbolically, though, unlocks a host of powerful ways to not only keep track of what's going on and see where the errors were, but also to check what is going on. Okay. We got there. It's been 40 minutes, we got there. That's the end of chapter 5, technically, in your book. I honestly don't know why your author split the two chapters up, okay? But now we're going to move into chapter 6. I really conceive of and think of in my head as chapters 5 and 6 just being one big chapter. Because what chapter 6 does is it does all of this all over again, but we're going to add friction. We're going to put friction into the mix. Okay? So before we start doing any, let's not do that quiz. Before we start doing any of that, we do need to talk about sort of, not what friction, everybody knows what friction is, right? It's that rubbing, right? That when two surfaces come into contact, okay? they sort of fight against each other. But we got to talk about the fact that we got to talk about how we write it down. And then we've got to talk about the fact that there are two different kinds of friction out there. And the two different kinds, there's static friction, and then there's kinetic friction. And there's slightly different rules that apply depending on which type you have. And the key thing that you need to remember is that friction is fun. You are going to get very tired of that pun because I'm going to use it over and over again. So fair warning, okay? The equation I've drawn on the board is the relationship between friction and what other force? Normal force. Notice that friction and normal force are related to each other through a constant that is called the coefficient of friction. That symbol that you're seeing there is not the letter U. It's really close. U as a letter, right, basically has one tail, like the little curvy tail part over here on one side, right? What you're seeing up there is the Greek letter mu, which is a U that has like an elephant trunk on the front of it or something, okay? So Greek letter mu, like mew, mew, like little kitty, okay? Well, it's spelled M-U. But basically, to write it, usually what I do is I give it that trunk and then I don't even lift up my pencil, right? So I tend to go long on it, but it can be kind of like that. Anyway, there's different sort of calligraphic styles for it. But that's what that symbol is, that mu right there. It's not U, it's mu. All right. Among other things that you will learn in this class is a new language, Greek. All right. So what the heck is going on here? Let's talk about the differences between static and kinetic, and we're going to do an experiment right now. I want everybody to take your hands, okay, put them together like this, okay, and just rub. Okay, so what do you feel? Feel heat. What you also are feeling is kinetic friction. Kinetic, you can stop, unless you want to warm your hands up. Kinetic friction, that word kinetic and static, refer to what the surfaces are doing relative to each other. It's important that we talk about what the surfaces are doing, not anything else that's going on. Because one hand is moving with respect to the other, we have kinetic friction. And as you found out, kinetic friction generates heat, which is thermodynamics, which is physics 4C. We're getting ahead of ourselves. Okay, do the same thing, only this time, what I want you to do is push your hands together hard enough so that when you try to slide it, it can't slide. So try to go like up and down. You'll feel your skin shift a little bit, okay? But there, that is static friction. And why is it static? It's not moving relative to each other, right? Okay, let's stop for just a second. Can we draw it? No. We can demonstrate it a lot, though. I am now talking about motion. Aren't I? Wait a second. Wait. Mr. Balogh. What are you talking? Are you talking about acceleration or velocity? If I'm saying it's not moving or it is moving relative to the surface, what am I talking about? Velocity or acceleration? Velocity? Isn't velocity easier to understand? Well, this is great, Mr. Balogh. Isn't friction easier? No. Okay, no, it's not, right? And let's see if we can't throw out some of the bad water that's in your brain. What kind of friction exists between a soccer player and the pitch surface as they go in for a slide tackle? Kinetic or static? It's kinetic. How do you know it's kinetic? Sliding, right? In American baseball, sliding into second base. I know enough about sports so you don't slide into first. Slide into second base. The player is sliding along the ground, right? That has to be kinetic friction because the player is moving and the ground isn't, right? It'd be more interesting if they played baseball that way. But anyway, right? They're sliding along the ground, okay? That's kinetic friction. You can take this following statement to the bank. It's never not true. Don't use no double negatives. Kinetic friction always acts against the direction of motion. If the player is sliding forwards, which way is kinetic friction pointed? Backwards. Kinetic friction always opposes the direction of motion. Okay? What kind of friction exists between the tires of your car and the road as you're driving along? Kinetic or static? It depends. I hope it doesn't depend. Yeah, how bold are your tires? All right, let's ask a different question. We'll get back to that one in a second, since there seems to be some disagreement. What kind of friction acts between your foot and the ground when you take a step? Static? This is where you guys see me fall off and die. Plant my foot, right? Step forward, right? What did my foot not do relative to the ground? It didn't move. I moved, but my foot, between my shoe and the surface of the ground, was there any motion? No. If there was, what would be happening? I'd be sliding or slipping or doing the moonwalk or something, right? I don't want there to be any slipping. When I plant my foot and I move forward, I don't want it to go woo, right? Okay? So static friction exists right there, even though me, the object, is moving, right? What do you have to look at? The planes of contact, right? Okay? The plane of contact between my shoe and the ground, those two surfaces are not moving. So this is static friction. Bonus. What direction is the force that I apply on the ground? Your choices are forwards or backwards. Okay? But what direction is the force that I apply on the ground as I step forwards? Backwards? Wait, I step and push backwards on the ground? According to the song, that means the ground pushes forwards on me. I went forward, but I had to push backwards on the ground, right? I see, good. I couldn't trick you there. Okay. So, floors are filthy. Yes?
Just like as a thought, what would the tread on a tank be?
Okay, good. So I'll answer that question in a second. So back to tires, which is going to be the same for a tank tread. Okay? Back to the tires between your car and the road surface. What kind of friction exists between your car's tire and the road surface? It better be static. Because if it's not static, what is your car doing? Sliding. Now, if you are into drifting and you have a car that can drift and that is like your competition style, then drifters, you guys know what I'm talking about, where the cars do those really cool donuts and stunts and things like that, right? A drift is taking advantage of kinetic friction, actually. Static and kinetic, they kind of drift between the two regimes, okay? But for normal, everyday, safe driving, you want static. Static? Wait a second, my car's going 60 miles an hour. Yes, it is. Your wheels turning around are going 60 miles an hour on the bottom surface of the tire, going 60 miles an hour backwards, which is exactly what the road is doing, isn't it? Top of your tire is going, right? Okay, but like static friction. Notice, we're not thinking about the motion of the object. What are we focusing in on? Where the two surfaces come into contact, right? Your tire comes around just like my foot, okay, and pushes backwards on the ground, and the ground pushes which way on the car? What is an anti-lock braking system on a car? Just from the title, what do you think it does? It does not let the tires lock, right? Anti-locking braking system. The old days, before these systems, if you slammed on the brakes, you could stop the tire from rotating. But the car was still going. What kind of friction exists if the tire is no longer rotating but the car is still moving? That would be kinetic friction between the tire and the road. That is a slide or a skid, okay? Kinetic friction is weaker than static friction. Most of the time. Some of the time. Okay, this is complicated. How many of you have ever tried to move a large piece of furniture, like a couch or a refrigerator or something that's kind of heavy, and you don't really want to pick it up because it's just, and so you just start pushing it across the floor, right? And you may have noticed as like you start pushing, okay, like you have to push really hard at first, but then as it gets moving, it's a little bit easier to keep going. You had to overcome what kind of friction? Static friction. And once it was slipping and sliding, it was kinetic friction. Not to mention the inertia was in your favor now because you had it moving, okay? Static friction can be stronger than kinetic friction. In fact, if you want to move a piece of furniture kind of properly across the floor, you can buy these things called furniture sliders. They're not wheels, they're just things that are like coated with plastic or Teflon on one side, and they're grippy on the other surface. You put them under each of the legs, and then it becomes much easier to slide that thing across the surface. You're reducing the amount of static friction between the objects so that you can get it going. Like, if we were to kind of graph what's going on here, right? And this would be like the strength of the friction over time. Static friction will vary. It'll change its amount to maintain that static friction, right? So if it's only a little bit, like if you're not pushing, if I'm not doing anything to this desk, right? It's just sitting here. I'm not pulling on it. The static friction is at a minimum. But if I start pulling on it, I'm not sliding it yet, but as I start pulling on it, the static friction has to counteract my pull, right? What's the acceleration right now of the desk? How do you know?
No change in motion.
The velocity's not changing.
I heard not moving. You didn't say that, right? I didn't hear it. It's because it's not changing its motion, right? Okay? But if I pull a little bit, then static friction will be a little bit. If I pull a lot of bit without it slipping, then static friction has to be a lot of bit, doesn't it? Yes. To keep the acceleration zero. As soon as I start moving it, it's not static friction anymore. It's kinetic friction, isn't it? So static friction will vary with applied force. It'll change its direction with applied force. If I try to pull it towards me, static friction is acting towards you. But if I try to push it towards you, which way does static friction point? Towards me. Like it's static friction wants to keep those surfaces in lockstep, and it will do anything, change its strength, change its direction to make that happen. And this is why static friction is evil. It's safe, but it's evil when it comes to analyzing what's going on. If the problem says there's static friction, you should panic because it can go wrong really fast. If it's kinetic friction, we know what direction it's acting. And in that like transition, what'll happen is like you'll have the static friction in this regime, okay? And then kinetic friction will more or less level itself out. It's kind of a constant. It varies slightly as you go, but like it more or less stays at one value while the object is moving. But static friction, do whatever it wants. So you'll often see books like try to clue you in. They'll write that, okay? And then they'll write like this. What are they trying to tell you? K is kinetic, right? And notice the coefficient is different. Static will be whatever. Okay, it'll always work. So the coefficient of static friction can go from 0 to negative to positive. Like it can be all over the place. Coefficient of kinetic friction generally is one number. Okay, and the direction. Notice I'm not writing down directions on any of these equations. These are just magnitude equations because we'll set the directions in our diagrams. Okay, I went looking for examples to do with friction in them. And so I asked the internet, can you give me an example of like, I mean, the thing that popped into my head was a slide. Like at the playground, right? You go down the slide. What's so fun about going down the slide? Whee, right? Okay, but the speed at which you can go down the slide is determined by the friction between your rear end and the slide surface, right? Between whatever clothes you're wearing. Growing up, we used to wear corduroys. Okay? And all the slides on the playground were made of metal. The coefficient of friction between corduroys and metal is like practically 0. Like it was better than ice, right? And we could get speed off of those slides. Nowadays, slides are made out of plastic. And we're using all of these corduroy is kind of a synthetic. But anyway, it's just not nearly as fun because they put bumps in the slide to slow the kids down because we got to keep them safe. Rollers?
Yeah, like each one so you can just really get going.
I love it. Mu sub S. Yeah, and mu sub K. So I asked the internet, give me an example picture, and this is what I found. Right? Here, civil engineers, civil engineering majors. This is my challenge to you. Remake society to this. Okay? Because society would be a lot happier, right? Just make sure the lawyers aren't involved. Because the lawyers ruin all the fun, right? Okay? Why is this not a thing?
Because there would be some jerks who just try to call them slime.
Still. You just take them out on your way down, right?
Survival of the fittest.
This can't exist because there's going to be some guy rolling down and break a leg.
But again,
Choice to either go
right.
down the
You have
slide
choices
or just
everywhere. There's just some things in life that should be. Okay? All right, so let's apply friction to our inclined plane. No, let's not, Mr. Balogh, say that we did. Okay, we could do that, but that would be lying. Okay, so there's my hill. Here is my, I don't remember, do we even say it was a tomato, or did I just dodge the issue? What object did we have last time?
Tomato.
Was it still a tomato?
Yeah.
Or a crate or something?
We're not having tomato. I don't like the tomato.
You don't like the tomato? You guys picked the tomato. It's haunting you now. Just like penguins are going to haunt you.
I want this tomato.
What? Scarf? A car. It's boring. It's boring. Dr. Orphy! Did she hear me? Dr. Orphy! That would be you. Can you give me an object sliding down a hill?
You could have a bowl, a wagon, my kids.
We're going with their kids.
Dr. Orphy's kid sliding down a slide. There we go. Thank you very much. Thank you very much. All right. Dr. Orphy, everybody, teaches engineering. All right. So Dr. Orphy's kid sliding down. Mass 1. Okay. Right. All right. Sliding down a hill. Down a hill. We know the kid is sliding down the slide, right? That means we know something about what kind of friction it is. What kind of friction is it? It's kinetic. Okay? Which way does it point? Opposite the direction of motion. Not acceleration, motion. Which way is the kid going? Down. Okay? So that means that the friction is pointing up the slope. It's kind of like automatic, isn't it? But notice the complexity that we've added here. We not only need to think about motion now, which is kind of easier, which feels good, but we also have to remember that acceleration is key in applying Newton's second law, and that's change in motion, right? Is the kid speeding up or slowing down as they go down the slide? Speeding up? Probably. Starts at rest, right? And then picks up speed and probably gets to some terminal speed eventually, right? But we'll not worry about that. So which way are we going to say the acceleration is pointed? Thank you, Dr. Orphy. Okay. Oh, she left. There is a group on campus that Dr. Orphy leads called the Society for Women Engineers. If you want to know more, come see me. It's a great group. They do fantastic things, and they have really good opportunities for careers and meeting people. It's really good. All right. Friction points up. Which way does the normal force point? Perpendicular to the surface, which means the normal force and that friction are what? They're perpendicular to each other. What direction is the normal force when I'm stepping on the ground? It's up, perpendicular to the surface, right? What direction was the friction? Horizontal, right? So on a slope, on a flat, which way does normal and friction always point? They're perpendicular to each other. Friction is the force that exists because the surfaces are interacting with each other in the plane of the surface. It's the only place it can act. And the normal force is there because the surfaces are in contact with each other, the perpendicular, right? So when we talk about the hill now, not only do we have to remember the normal force, we've got to remember friction. Those are both, the objects for both of those things come from the surface of the hill. All right, what other forces are acting on Dr. Orphy's kid as they slide down the line? Okay, so the earth and gravity, right? So we make sure we come in here and we have, so we know where the normal force comes from the slide. We know where the friction comes from the slide. We know where gravity comes from the earth. Are there any other objects pushing or pulling on Dr. Orphy's child? No. No air resistance. Okay? But it's not a physics slide anymore, right? This slide has friction. We're getting closer to reality, aren't we? The closer we get to reality, the more you're going to beg for mercy. Yeah. Okay. So, what do we do now? Where's the x-axis? Which way is it going to be? Down the slope. Why? Because that's the direction we said acceleration was. Okay. So there's only one object, which is great. So that means in the x direction, I have m times a equals, and in the y direction, I have m times a e. But what is the acceleration of the y going to be because I said it? 0. You getting the feeling for like how we kind of do this? Right? We want to try and simplify the math? All right. Okay, so we got components, right? What's this one going to be? We've done it like 3 times now. Sine. What's this one going to be? Cosine. You can go back and look at the other diagrams for the angles and blah, 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 blah. That didn't change, right? Didn't change. Okay. How many forces are there in the x direction? Dos. They are F and mg sine theta. In the y direction, how many forces are there? Looks like 2. n and mg cosine theta. I'll go back and do the signs. F, positive or negative? Negative. Why is F negative? Mr. Bale is pointing up, and up is always positive. No, it's not. Look at your direction. Look at your coordinate system. Positive x is down the slope. F points up. That means it's negative. Mg sine theta, positive or negative? Positive. Snowballed you already. All right. Normal force, positive or negative? Positive. And then negative. All right. Solve for the acceleration. Okay. How many unknowns? I got two equations, right? How many unknowns are there? Well, let's assume that we know the mass. We know mass, we know theta. We know, of course, little g. Okay. So we know this. So mass is, acceleration is an unknown. What have I got here? I got 1, 2, because I don't know F, right? And then 3 for the normal force. There's 3 unknowns. And 2 equations. Is this solvable? No. What do we need? If you have 3 unknowns, minimum, how many equations do you need? 3. Where's the third equation? You forgot how fun this is going to be. Don't forget how fun friction is. Because what does the fun equation do? It links together all of our unknowns that we basically want to get rid of. We want to get rid of F and N, right? So that we can get to A? Or, of course, there's tons of variations on the thing. Maybe they give you the acceleration in the problem, ask you to find the coefficient of friction. Like, there's lots of ways that they could ask at this point, right? But the point is, now I've linked together everything, and I'm okay, so the y equation finally has meaning and purpose? What does the y equation tell us? Tells me that, and if I solve for n, I get mg cosine theta, don't I? Move the cosine theta over to the other side, becomes positive, reverse the direction. We solved for that one before, and when we had no friction, it didn't really help us, did it? It was just kind of there along for the ride. It wasn't really necessary. Now that friction is involved, we need that equation, don't we? Because it's fun. So now I take this, so this came to here, this goes up here, which turns into F equals mu times mg cosine theta. And that F goes where? Every mathematician just died. Because I've drawn arrows in my math. Did you have a math teacher that told you you couldn't do that? My math teachers never let me draw arrows to connect the dots. I think it made me the poor mathematician I am today. Because if I could draw arrows, it's all clear now. And they don't yell at you? No. You have better math teachers than me. All right. What am I left with? MA, and some of you are looking at this going, Mr. Bale is the biggest piece of garbage I've ever seen in my entire life. Like, some people's brains work this way, others don't. MA minus mu mg cosine theta plus mg sine. Where'd that minus sign come from? There was a minus sign right there, right? So I had to carry that down. F was this thing, so it, right, went in there. The mg sine theta was along for the ride. It was just already there, right? And now can I solve for my acceleration? See, it looks like it's the only unknown I have. What cancels? It's in every term. Like it. Okay, so my acceleration is, and yes, my math teacher's yelling at me, so we'll do g sine theta minus mu cosine theta. I factored the g out because it was everywhere. Okay, so that's what I got, and we check it. Yes?
What
Sure. Don't care. Because I got a result, right? Solve for the acceleration. So if I wanted the acceleration, I'd have to know mu, right? But if I was given the acceleration, I could then find mu. Lots of different ways to go, right? But how do we check this? Like what angle? What's going on? First thing to check is, what is friction doing? What is this term that's got the frictional coefficient in it? What is it doing to the overall acceleration? It's something minus the friction. Is friction causing this kid to slide down or to accelerate less than if friction weren't there? Yes, that is what's going on, right? Because a slide coated in Teflon, way better than any others, right? Teflon being the not sticky stuff, right? Okay, so we could play with this, right? What happens if what's the coefficient if the surface is frictionless? It's 0, right? So what is, if I put mu for 0 in there, I just get g sine theta? Where have we seen that before?
Go down slide.
We did this with the tomato back in chapter 5, right? The frictionless hill was g sine theta. And we got g sine theta when we did this whole thing and we eliminated friction. Are we on the right track? Looking good. All right. Angle. Well, we know sine theta, steeper wins. Okay. But what happens to cosine theta as you get closer and closer to 90 degrees? Is the cosine getting bigger or smaller as it goes to 90? Smaller. Is friction having less and less of an effect as the slide gets steeper and steeper and steeper? I like this, right? This is consistent with the physics I know and understand from the playground. That crucible of survival that took place between lessons in elementary school. My happy place was in the classroom because all the bullies were under the eyes of the teachers. It was survival of the fittest out on the playground, wasn't it? And I went to a school where they didn't have wood chips under the monkey bars. You know what was under the monkey bars at my school?
Concrete.
Asphalt. I survived. So will you. We'll see you on Wednesday. Get into chapter 5 and 6. Just get into them. Start working on it. You need time to sort all this stuff out.